So, as I said in the last lecture, this one is going to be a little more theoretical. What I'm going to do here is show the correctness of Kruskal's algorithm. In other words, I'm going to show that if we start with a graph and we generate a new graph by following Kruskal's steps here, then the output is a minimum spanning tree of the original graph. Now, to do that, I'm going to need one more theorem that we haven't talked about yet. If you start with a spanning tree and you add an edge to it, that creates a new graph which has a unique circuit. Right? It has one and only one circuit in it. Now, I'm not going to prove that. The proof of this is actually relatively straightforward, so I'm going to leave this as an exercise. You'll also see it in the classroom on the website. So to show this, we need to show three things. First, that the graph is circuit-free and connected, which is going to make it a tree. And second, or third on the list here, that the output has the minimum possible weight. Okay, we get the circuit part almost for free. The algorithm itself specifically forbids adding any edges that would create a circuit. So if we follow the directions, there can't be a circuit in the graph anywhere. To see that the result is connected, let T be the subgraph produced from G by the algorithm, right? And let G1 and G2 be two disjoint connected components of T, like what I've got in the diagram here. Since the original graph is connected, there must be a path in G between any 2 points in those components. And there must be at least one edge in that path that is in either of them because we assume that they're disjoint. Now, adding this edge won't create a circuit because deleting an edge from a circuit doesn't leave the resulting graph disconnected, and we have two disconnected components here. So this means that some edge connecting the two components must be in T, or the edge set in E in the algorithm would be empty, so the algorithm wouldn't have terminated yet. So showing the minimum weight part gets a little tricky. So and I want to be clear on what I'm going to try to do here. At this point, I know nothing at all about the weight of T, other than it has one. Right? So what I'm going to do is I'm going to say let T be the output of the algorithm, and let K be a minimum spanning tree. And I'm going to make some assumptions about K. First, I'm going to assume that K is different from T. Right? And second, I'm going to assume that K is the minimum spanning tree with the maximum number of edges in common with T. Right? Because minimum spanning trees, they're not unique. Yeah, I mean, think about a square. If you have a square where all 4 edges have the same weight, that graph has 4 different spanning trees. You get one for each edge you can remove. Okay, so K is a minimum spanning tree. It's not equal to T, and they have the maximum number of edges in common. I'm going to do this by contradiction. Right, so ultimately what I'm going to show is that K in fact does have to equal T, which means that T has the minimum weight. Okay, so here's how I'm going to do it. Because the graphs are different, they're not equal, there must be an edge in T that isn't in K. Call that edge E. Right, now I'm going to take that edge and I'm going to add it to K. Now this is where that theorem I talked about on the first slide comes in. Right? Adding this edge creates a circuit in K. Now I'm going to let F be the edge in that circuit that isn't in T. Right? And such an edge has to exist, because if it was in T, then T would have a circuit. Right? But T doesn't. So there has to be an edge in K, specifically in this circuit that's not in T. Okay, now here's what I'm going to do. I'm going to make a new graph. I'm going to let T prime be the graph made by taking K, removing F, and adding E. Right? T prime is connected, since to build it we removed an edge from a circuit. And in a connected graph, removing an edge doesn't make it disconnected. Since this graph has n vertices and n minus 1 edges, it must also be a spanning tree for G. Okay, now let's talk about the weights. Right? The weight of K prime is equal to the weight of K plus the weight of E, the edge that we added, minus the weight of F. That's the edge that we removed. Okay. Also, the weight of E is less than or equal to the weight of F. If F had been added before E, that is, it had a lower weight, then adding E would have created a circuit, and obviously that's not allowed. So the weight of F must be greater than E. It has to have been added after E in the algorithm. So here's what I'm going to do. I'm going to rearrange the right side of that left-hand equation. I'm going to make it the weight of K minus the quantity of the weight of F minus the weight of E. Now the weight of F minus the weight of E has to be positive. Right? This means that W of T prime, W of K prime, is less than or equal to the weight of K. Well, K was a minimum spanning tree. It has the minimum weight. This means that the weight of T prime actually has to equal the weight of K, which means that K prime is also a minimum spanning tree. And there's the contradiction. K prime has one more edge in common with T than K does, which contradicts our assumption that T and K have the maximum number of common edges. This means that our original assumption that T and K are different must be false, and since T is equal to a minimum spanning tree, it must itself be a minimum spanning tree, and that's what I wanted to show. So what's next? Well, there are other algorithms besides Kruskal's algorithm for finding a minimum spanning tree. In the next lecture, we're going to talk about something called Prim's algorithm, which has the same goal, to find the minimum spanning tree of a graph, but as you'll see, it does it in a very, very different way.